Okay, we're in section 3.5 now, and we're talking about a topic called implicit differentiation. Implicit differentiation naturally follows from the chain rule. This is why this section comes right after our section on the chain rule. So in order to understand implicit differentiation, first thing we need to do is talk about the difference between a function that is given in explicit form versus a function that's given in implicit form. So typically when we think of functions, we're thinking of them in explicit form. And explicit form is when the function is written this way: y equals some function of x. So literally what I mean by writing this is that the function is presented as an equation, and we're writing y, understanding y to be the dependent variable, and we define it to be some function of the variable x, which is the independent variable. The key thing here is that the y is isolated on one side of that equation. So here are a couple of examples of explicit equations, functions given in explicit form. Y equals x over natural log of x, or y equals sine of the square root of 1 minus x squared. The key thing here is that y is isolated on one side of that equation, and on the other side we see a function only involving the variable x. Okay, so that y is defined very clearly in terms of x. The implicit form for a function is also represented as an equation, but it's written in such a way that the y variable is not isolated. So for example, x squared plus y squared equals 25. This is called an implicit equation. We can think of y as a function of x, but y is not being isolated. Another example, tangent of x plus y equals x times y. This, if we can choose to think of y as a function of x, but y is also not isolated here. Okay, now the important thing to note when it comes to implicit equations versus explicit ones is that the equation itself, just taken as an equation, might produce a graph. In fact, oftentimes will produce a graph which fails the vertical line test. Now from algebra, we know that the vertical line test is a test that you can use when you're looking at the graph of some equation to determine if y is a function of x. So if I'm looking at this, this is the graph of x squared plus y squared equals 25, this example right here. We know from algebra that this is the equation of a circle centered at the origin with a radius of 5. And it's very clear that this would fail the vertical line test. Any vertical line that I put through this circle will hit it in more than one place, unless it's at one of these points of tangency over here. So that would indicate that y is actually not a function of x, even though I just set up here that we could think of y as a function of x. And the reason why I'm saying that you actually can think of y as a function of x is because we can think of the curve or the graph given by this equation as more than one function being represented simultaneously. Notice if I took this circle and I broke it into two pieces, its upper semicircle and its lower semicircle, which I've shown down here, by themselves, each one of these is a function because each one of these graphs passes the vertical line test. If I wanted to represent each one of these algebraically, I could work directly with this equation and try and solve for y. So the idea there is to take this implicit form for the function y and put it into explicit form, which again, that's just solving for y. It's not hard to solve this for y. It's just two steps. Subtract x squared from both sides and then take square roots of both sides. However, you know that when you take square roots of both sides of an equation, you pick up a plus or minus. So this is not actually just one equation. It's two equations. Y equals the square root of 25 minus x squared, and y equals negative square root of 25 minus x squared. Each of those equations gives me one of these semicircles. So taken together, I have a full circle. And this equation right here is taking both of those explicit equations, those explicit functions, and putting them together to give me one entire circle. So in that sense, really, let me come back up here. if we're looking at a function given an implicit form, so I'm thinking of y as a function of x, even though y is not isolated here, then the implicit form given here, this equation, may actually represent y as a few different equations, or sorry, as a few different functions of x simultaneously. In this case, two functions of x, one giving me the top semicircle, one giving me the bottom semicircle. Okay? Now, in this case, I was able to analyze this a little bit more by isolating the y, and like we said, putting it in explicit form. But oftentimes, it's extremely difficult or even impossible to do that. An example would be this one right here. You're not going to be able to successfully solve for the y in this equation right here, the way that we did here. With that said, excuse me, we still need to be able to do calculus with functions that are given to us in implicit form. There's lots of instances where we have to be able to do that. In particular, because we've been talking about derivatives and slopes of tangent lines and things like that, I may want to find the equation of a line tangent to a curve that's not a function by itself. So like a line tangent to this circle at some particular point. One way of doing that is to try and solve for y like we did here, and then use my derivative, use the derivative to find the slope of that tangent line, and so on and so forth. But in cases where I can't isolate the y, I need another way of finding the derivative at a particular point on a curve. So that's where implicit differentiation comes into play. Okay? And I sort of talk about that up here. Now, the key behind implicit differentiation, which we're going to talk about, is again, even though the y, as we're seeing here, is not isolated, I'm choosing to think of it as a function of x. So this x squared plus y squared equals 25, I can think of that as x squared plus y of x squared equals 25. I'm thinking of y as y of x. I wrote that right here. And the reason I'm writing that extra notation in there, again, is to remind myself that this is a function of x. Now what I'm going to do, if I want to find the derivative, which we're going to do in this next example here, I want to differentiate both sides of this equation with respect to x. Because now that I'm thinking of y as a function of x, I can think of all of this left-hand side as just a function of x, which now I can do the differentiation. And the key thing here is that because y is not isolated, but instead something is happening to it, it's being squared, I think of this as a composite function. Y of x is my inside function, and then x squared, the second power that I'm raising it to here, represents the outside function. Differentiating that with respect to x requires the chain rule. So let's come down here, and we're going to do a couple of things. So we're given the same circle, x squared plus y squared equals 25. And we want to do a couple of things. First of all, we want to find dy dx. We want to find the derivative of this, of y with respect to x. Then we want to use the result that we get there to find the equation of the tangent line to this circle at the point -4, 3. So for this first example, I'm going to continue using that y of x notation, but in all following examples, we're not going to do that because in practice, we don't actually write y of x. We just implicitly, as the name implies, think of y as a function of x. So I'm just going to, for this first example, to help illustrate what's really going on here, we're just going to write this. Now what I'm going to do is differentiate both sides of this equation here with respect to x. So d dx, both sides. On the left-hand side, the derivative of x squared with respect to x is just 2x. Here, we have to think of this like the chain rule. So the outside function is another x squared function. That means I'm going to have plus 2 times the thing that was on the inside. So my inside function, which is y of x, But then I have to multiply by the derivative of my inside function, y prime of x. Okay? Over here, I have 25, which is a constant. Differentiating that with respect to x would give me 0. Okay? Now the next step is to solve for y prime. I'm going to isolate y prime. So notice if I divide both sides of this by 2, I can cancel those 2's out. Then all that's left to do is subtract x from both sides and then divide by y of x, giving me this. Y prime of x is equal to negative x over y of x. Okay? Now, like I said, we typically don't write y of x even though we're thinking of it as a function of x. As long as you're thinking of y as a function of x in the background, it's more efficient to leave this of x thing off. So really, I'm going to write this way. dy dx equals negative x over y. Okay? Now I want to point something out here. The derivative of this function, the dy dx, depends not only on x, but also on y. And the reason for that, if we come back here, so we have more to do here, but let's look at what we're asked to do in the second part. We want to use our result to find the equation of the tangent line at the point negative 4, 3. Okay, so back here in my circle, let's just say that this is negative 4, and that's 3. So that's the point negative 4, 3, right? If I got my derivative and all I had was a function of x, then that indicates that if I want the slope of a tangent line to this circle at a particular place, all I have to do is plug in an x value. But the problem with that is that the circle here is not actually a function. So let's suppose I were to write something slightly different than this. If I said find the equation of the tangent line to the corresponding circle when x equals negative 4, instead of the point negative 4, 3. If all I said was when x equals negative 4, it's not clear which point on the circle I'm talking about, because notice there are 2 points on this circle that have negative 4 as an x value, and I can see that each of these will have different slopes for their tangent lines. One is positive, one is negative. So it makes sense that my derivative should depend not only on x but also on y, because that's how I'm able to single out which of these points I'm looking for a tangent line to. So coming back here, I've found dy dx, and it's a function of both x and y. It depends on both of those. Now I need to find the equation of my tangent line. So in order to do that, I'm using the point negative 4, 3. I have an x and a y, both of which get plugged into this. So the slope of my tangent line is going to equal negative x, which is negative 4, or positive 4, over y, which is 3. Okay? Which implies that my tangent line is going to have the equation y minus 3 equals x, 4 thirds x minus negative 4, or x plus 4. Okay? Now notice we ended up with a positive slope here, which is good. That's what we would have expected, because we were looking for the slope of the line that was tangent to the circle at negative 4, 3. And from this diagram, I can see that that would have given me a positive slope. Negative 4, negative 3, which would have been the wrong point, would have given me a negative slope, which is not what we were expecting to see. Okay? So one example down, this process is what we call implicit differentiation. Notice that what we're doing is we're taking the derivative without needing y to be isolated first. Okay? And it's really the chain rule, which we used right here, that's allowing us to do this. So here's another example, a little more complicated. This time it's only asking me for dy dx. I'm not looking for a specific tangent line or a specific slope anywhere. But I have... I just remembered something I wanted to do, actually. Let me come back to this. I'm jumping the gun a little bit. So we have our answer here. I forgot that I left this space down here to do something specific. I wanted to show that the result that we got is the same result that we would have gotten if we, instead of using implicit differentiation, tried to isolate y in the original equation here, and then take the derivative of y in its explicit form. So let me actually do that. Up here, because the point -4, 3 is on the upper semicircle, then I know the equation that I'm looking at is y equals the square root of 25 minus x squared. Okay, so if I was going to try and get this same result, but without using implicit differentiation, I would first need to isolate the y, which we showed before gives us two different equations, y equals plus or minus the square root of 25 minus x squared. Determine that because we're going to be looking for the derivative at a specific point which shows up on the upper semicircle, I want the positive of those two. Now I can take a derivative, dy dx. Now this derivative requires the chain rule, right? Because I have a composite function, 25 minus x squared to the 1/2 power. So its derivative, I would take the derivative of the outside function, which would be 1/2, leave the inside alone, 25 minus x squared to the -1/2. So here I'm using my power rule. Then I multiply by the derivative of the inside function, which would be -2x from this guy right here. Okay. Now do a little simplification. So the -2 and the 1/2 would multiply together to make -1. So we'll just call that negative. I'd have an x left over. And then -1/2 here implies that I have a radical in my denominator. So I would write that as square root of 25 minus x squared. Now, you might look at this at first and think, well, it looks similar to what we got up here, but it's not exactly the same. But these two expressions are the same, because if you look at what's in your denominator, the square root of 25 minus x squared, that's what y was defined to equal. So this could have been alternatively written as -x over y. Same result, right? Implicit differentiation, though, is more efficient because I didn't need to go through the work of isolating the y first. And it turns out that the derivative itself was actually a little easier to take. All I took was a derivative of two power functions, essentially, using the chain rule here, whereas here I had more complicated functions to work with. So now that we've sort of established that we're getting the correct results, let's do the example that I mentioned up here. So here we have another equation where a function y is given implicitly in terms of x, but we don't have the y isolated. Furthermore, it would be really difficult to isolate the y in this equation. It's more complicated than the circle that we dealt with in the last example. So we're not going to bother isolating y. Instead, we're going to differentiate both sides of this with respect to x. X cubed minus xy squared plus y cubed equals dx of 1. Now on my left-hand side, I'm going to do this term for term. So the derivative of x cubed is 3x squared. Here, I think of this as a product of two functions. So I'm using my product rule, x times y squared. So my product rule would say take the the first function times the derivative of the second. So let's do this, minus, and I'm going to put this in parentheses because when I do the product rule on this term, it's going to produce two terms, and I need to make sure the subtraction is being applied to both. So x times the derivative of my second function. And again, this y squared, it's not just a power function. Remember, you're thinking of y as a function of x in its own right. So it's a function of x raised to a power. It's a function within another function, requiring the chain rule. In this case, y is the inside function, and x squared is the outside function. So using my power rule, I'd have 2 times my inside function, but then I need to multiply by the derivative of my inside function, which is y prime, or dy dx. Okay? Now over here, I have y cubed. And again, I'm going to be thinking of that. Oh, I'm jumping the gun again. I only did half my power rule. So I did my first function times the derivative of the second. Now I need my second function times the derivative of my first. X, its derivative is just 1, so I'm going to have plus y squared as a result there. Okay? Derivative of this guy would be plus 3y squared, but then again, because it's the chain rule that I'm really using here, I multiply by the derivative of my inside function, which is the derivative of y, dy dx. That's equal to 0 because I'm differentiating a constant there. Okay, so again, the goal here is to solve for dy dx. That's what I'm trying to find. And just to recap, every time I'm differentiating something involving a y, you'll notice it's spitting out a dy dx in that process. And again, I've said it several times, I just want to drive the point home. This is because of the chain rule, okay? So let's distribute that minus sign in. 3x squared minus, I'm going to write this as 2xy dy dx plus y squared plus 3y squared dy dx equals 0. In order to solve for dy dx, I want to collect all of the terms that contain a dy dx on one side of my equation and get everything else moved over to the other side. So I need to subtract the 3x squared and the y squared over to the left, which will give me this, negative 2xy dy dx plus 3y squared dy dx equals negative 3x squared minus y squared. Okay, then I want to factor a dy dx out. So I have dy dx. I'm going to change the order of these terms and write the 3y squared first minus 2xy. I like to have a positive term first if possible. 3x squared minus y squared. Finally, I divide by the expression in parentheses here so that I end up with this, dy dx equals, in fact, what I could also do, you don't need to do this, but I can factor a negative out of both of these terms and bring it all the way out to the front of this quotient that I'm going to end up with, 3x squared plus y squared over 3y squared minus 2xy. Okay, so this is my answer. And once again, notice that the derivative gives me some expression involving both x's and y's. That's for the same reason as what we saw in the last example. The graph of this, which if you use something like Desmos, you can put this equation straight into Desmos and it'll graph that implicit function for you. You'll see that it's a curve that fails the vertical line test. So a single x value, when plugged into this, may correspond to more than one y value. So the y value is also necessary to determine the slope of that tangent line. We'll go ahead and do this next example on part 2.